there are some milestones and generators that are making us think that we have to make this intense and proactive testing on the high-speed Ethernet networks. So just for your information, a couple of notes here. You all know that we have like a traffic explosion at the moment with all the video consumption, internet, online gaming, this explosion of mobile devices. So these type of things are obviously driving the demand to have more and more bandwidth in our networks. And just to give you one figure, we are talking here about exabytes. If you see in the axis, we have exabytes per month. So just for your information, an exabyte is 10 to 18 bytes. So just for you to dimension the whole thing. And another little figure that you can see in there in that exponential curve is that, for example, in 2015, we are going to have double number of devices than the size of the entire population in the world. So that's something really, really impressive, and some numbers to kind of, understand why do we need to have really powerful and ready network, high-speed networks in order to support all this traffic that we are going to have in the coming years. So let me use this laser pointer, which is always convenient. So this is the typical example of an enterprise network today. We are talking about traffic generation, and obviously in order to support all this traffic in the enterprise network, we need to have a modern infrastructure, right? That is going to be very likely in the present, at present, and in the future, copper and fiber cabling, right? So what you can see here in this picture is basically what we can call the low-speed part of the network, the traditional LAN network, which is typically interconnecting devices to the desktop at either 100 megs or 1 gigabit Ethernet that is nearly 100% copper, right? There is no fiber going to the desktop yet. And then obviously these devices have to be connected to some access switching network that are after that going to be connected to an aggregation network that leads to a router that goes to outside, to the wall outside, and connects to the internet. So together with this part of the network, we used to have the storage area network, the SAN network, which is basically the piece of the network where we used to store all the data, information, all these storage places where we typically have, or we typically need, very low latency in the network and very fast and quick access to the data and information, right? So possibly in the parts of the desktop and also possibly in the storage area network, the infrastructure that we are going to need is kind of well-defined. In the desktop, we are working typically with copper. In the storage area network, typically with fiber. But then there are other parts in the network where we have, 110, 40 gigabit Ethernet, where we are going to decide if we want to be or we want to go with electrical cabling or with optical cabling. So this is what we are going to review in today's presentation. Actually, in this slide, we show some of the standards, right? Ethernet standards for fiber and copper that we have at the moment. So the first thing that you can get from this slide is obviously copper came first in the early 90s with this coaxial solution, 10 base T, starting with coaxial and then with twisted pair. The T means twisted, so this will be the first twisted pair solution. And after that, all the fiber standards were coming up. And actually, the fiber standards caught up very quickly because, as you notice, things like the gigabit Ethernet or 10 gigabit Ethernet, and now the 40 and 100 gigabit Ethernet is fiber, right? So, the trend is that for future speeds, fiber is going to be, leading in the market in terms of cabling. So the thing that you have to know first, or you have to get from this slide, is that today we have standard defined for Ethernet applications for 40 and 100 gig. We don't have such a standard, right, for copper yet. And this is some point that we are going to discuss a little bit later in the copper section. So copper versus fiber, what is the path to move forward? So what is better, copper, fiber? There are some cons and pros when it comes to compare fiber and copper. Obviously, we have some advantages with the copper cabling. Like, for example, it's a well-known technology, an understood technology. It's typically very easy to install and terminate, very easy for managing the max, the changes and updates in the networks. It supports other technologies, like in the case of power over Ethernet. This is a technology that can run on copper cables. And another important thing to consider is that it's backwards compatible with lower speed, so it supports auto-negotiation. On the other hand, we have the fiber that obviously has many benefits as well, although it's typically, as we see in the market today, is less understood. It's like a newer thing that still needs to get some more knowledge in the market in order to be understood. It's a bit harder to install, terminate, but on the other hand, it can support higher bandwidths. We can say that fiber has kind of unlimited bandwidth, and it's obviously providing more density in terms of ports, right? So in the same space, we can fit more ports if we are working with fiber than if we are working with copper. And then we have to look at factors like the heat dissipation, the power, port density. So at the end of the day, it's up to the network designer and up to the network owner to decide if the infrastructure is going to be copper or fiber. And we are going to address all these kind of considerations, right, that you need to take into account whenever it comes to test high-speed networks for either copper or fiber. So let's get started with the fiber part, right, fiber considerations. And we are going to start with some information about the standards. So this is possibly the most important slide that you're going to see in this session today, right? This is representing basically the Ethernet specific performance requirements, right, for the different Ethernet speeds. So in this table we have, in the columns, we've got the different Ethernet speeds. This is 1 gigabit Ethernet, 10 gigabit Ethernet, and 40 and 100 gigabit Ethernet standards, right? And this is obviously fiber, right? So as I said at the beginning, we don't have yet defined 40 gig or 100 gig over copper. So this table represents the Ethernet standards for fiber, right? And in this part of the table, you have different fiber types defined in the standards: OM1, OM2, OM3, and 4, right? So basically, what we are representing here is the performance requirements in terms of loss, dBs, and length for each of these technologies or each of these speeds of Ethernet, right? So if we look at the 1 gigabit Ethernet application, we've been traditionally working with OM1 and OM2 fibers, and these have been traditionally the budget, let's say, available for accomplishing the channel requirements in gigabit Ethernet link, and this is basically the length, right? So if we move to other cable type like OM3, we can consider OM2 and especially OM1 as a legacy fiber. This is installed at the moment in many Ethernet networks, but typically the installations, the new installations that we are doing today in today's networks are either OM3 or OM4 fiber. So what you can see in this OM3 is basically, first thing that is going to be able to support 10 gigabit Ethernet, right, applications, and the tightening requirements, that the budgets available that we have for accomplishing the channel maximum channel attenuation are going down, are getting from 4.5 dBs to 2.6 dBs if we are working in A50 nanometers, right? So this is kind of the takeaway of this slide. If we move on to the different applications, fiber types and speeds, and we want to start touching the 40 and 100 gigabit Ethernet, we see the same thing happening here. So in these OM3 or OM4 fibers that are widely installed today, the requirements of the Ethernet standard for such a fiber are, in the case of OM3, are going from 2.6 dBs of maximum attenuation in the channel for 10 gigabit Ethernet to 1.9 dBs in 40 gig or 100 gig Ethernet. So this is really the challenge, right, that we have in new generation networks for 40 and 100 gigabit Ethernet. So the budgets are getting tighter and tighter, and it's going to be more complicated to actually achieve these requirements. We are going to see how, from my testing point of view, how we can give some tips and some advice in order to make sure that you are going to accomplish these budgets available in order to perform a proper installation. So if we look at the generic fiber performance requirements, this is literally information extracted from the TIA standards. What you have is basically that for the slope, or in other words, attenuation, you have a definition for each of the fiber types that we represent here, multi-mode and then single-mode fibers. You have an attenuation, right, which is different for different wavelengths. So in the case, and we are going to focus on multi-mode, in the case of A50 nanometers, you have an attenuation, maximum attenuation allowed of 3.5 dBs per kilometer, and then for 100 nanometers, which is the second typical wavelength that we use in multi-mode networks, we have a maximum attenuation allowed in this fiber cable of 1.5 dBs per kilometer. Then if we look at the kind of components of this fiber optic network, we have a maximum loss allowed as well per connector and per splice. So what the TIA standards say about this maximum loss allowed is that we are going to have a maximum of 0.75 dBs per connector and 0.3 dBs per splice. This is what the standard says, right? But if we look at the real world, it's a bit different, we can say. So a connector in the field, a good connector, should be typically in the range of 0.25 dBs of attenuation. That would be a good connector. And in terms of splicing, we see in the market today very good splicers that are able to splice fibers having nearly marginal attenuation of 0.01 to 3 dBs, right? So as I said, the real world is much different than what the standards say today. But you know, in this slide, we just wanted to represent what the current TIA standards are using today as a reference in terms of testing and performance requirements. So some things that you will need to consider in new generation networks, optical networks for 40 gig and 100 gig, is this new type of connector. So multi-fiber push-on pull-off connectors, MPO or MTP in some other scenarios. So you typically see single fiber connectors, right? The typical ones that you know, LC, FC, SC, E2000, etc. That means that you're going to have one single fiber per connector. In this new generation of connectors, you are going to have multiple fibers in a linear array, right? We have a little picture here, a representation of how this MTP MPO connector looks like through a microscope. And typically you're going to have, as I said, 8, 12, 24, 48, etc., different fibers in the same connector, right? So as you can imagine, this is really a breakthrough because we can dramatically increase and enhance the port density in especially places like data center where we really need, to take advantage of all possible space. So this is really a great thing to have if we compare with typical single fiber connectors. So regarding these NTP MPO connectors, they are usually used in breakout cassettes, that the ones that you have here in the picture. And basically these connectors are on one side connecting a couple of one or two MTP connectors, and then on the other side, on the rear part of the box, what you have is basically the fibers split in single fibers that are typically either SC or LC connectorized. So this is very common now in 10 gigabit Ethernet networks, and is going to become more and more popular for future 40 and 100 gig Ethernet networks. The other kind of setup that you will see typically in data centers is direct fibers are connecting MTP MPO connectors in a patch cord cable like this. So if we are talking about 40 gig Ethernet, we will be typically using a MTP fiber with a connector with 12 fibers on it, and 8 of these 12 fibers will be active fibers working in couples in order to receive and transmit. Same thing, same kind of a scenario for 100 gigabit Ethernet, where we typically have 10 lanes, in other words, 10 active fibers in order to achieve this communication of 100 gig. So something that we need to consider regarding these MTP MPO connectors is obviously these are going to be great, right? In order to especially increase the density of all the ports that we have in our enterprise network or data center. But on the other hand, these connectors are the source of many problems. And we'll see what that means in terms of contamination in fiber optic surface. So what is the typical enterprise fiber installation? Well, this is the typical scenario that you're going to have, for example, in a data center, where you want to connect a switch that is connected or is located in the technical room, and you want to get to a router that is in a, possibly even in a different building in a data center. So what you typically have is that this switch is going to be connected through a duplex fiber patch cord to an optical patch panel, and then this will be, let's say, the long run which connects the two optical patch panels between the two different telecom rows. So after that is the same thing between this optical patch panel and the router. We have a duplex fiber patch cord that is going to allow that connectivity, right? So a couple of things to consider here. First of all, if we want to compare this with a traditional copper scenario, where we have what we call a channel link and a permanent link. A permanent link will be in copper. The portion of the cable that is not going to be disconnected, let's say, is going to be fixed in the network. This will be from this patch panel to the other patch panel. That will be the equivalent in copper, and then the entire channel will be the whole fiber link from the router to the switch. Okay. So one thing that you have to consider for fiber optic networks with this setup is that obviously it doesn't make any sense to talk in this case about permanent link testing for fiber. Why? Because if we want to measure the permanent link on this section of the fiber, we will be still missing some attenuation, right, that is coming with the connectivity and the fibers that are connecting these other pieces of the network. So unlike what happens in copper networks, when working with fiber Ethernet links, we cannot talk about permanent link certifications. We need to talk about channel link certifications that are related to the tables that we have seen before. Another thing to consider is the use of these MPO or MTP cassettes that obviously are going to add or are going to have associated loss, extra loss that we are going to be facing, and in many cases they are going to be bringing a lot of issues into the installation if they are not dealt, they are not treated properly in terms of especially fiber inspection, as we said. So typical issues that we are going to face in these cassettes are the contamination. So we've been talking about the contamination in the previous webinar delivered by Paul Avison, and basically, you know, you have to know by now that most of the issues that we have in fiber optic networks are due to contamination in fiber optic connectors, right? And approximately 80–90% of these issues can be, you know, quickly resolved if we, you know, proactively inspect and test the fiber connectors before we make any connection. And this is not going to change from single connector fibers to multi or single fiber connectors, sorry, to multi-fiber connectors. So the situation is going to even get worse, because in this case you are going to have multiple fibers in the fiber connector, and actually you need to inspect and you need to test each of these fibers. So as you are all aware, we have a standard that is the IEC 61300-235 that is basically normalizing and standardizing a criteria in order to inspect a fiber connector end face and determine if this fiber is in good conditions or not to be connected, to be mated to another fiber. So as I said, if you were in our last presentation delivered by Paul Avison, basically you understood the way that this standard works, and basically you understood that this standard is defining kind of a criteria. It's going to quantify, it's going to qualify the different particles, defects, and scratches that you find in a fiber optic surface, and it's going to assess, right, if this connector is in good conditions or not to be connected. So according to this criteria that is well defined in the standards, in the IEC standard with tables like this, you're going to give a pass or fail for such a connector. That means that you can or you cannot connect this specific connector in those conditions, right? So very important to understand that this is going to be one of the main factors, one of the main issues that we are going to have in this connectivity. And I am coming back now to the table that we saw at the beginning of this presentation with all these type requirements, where if you have, you know, some of these dirt particles on the fiber end face, you may be creating much more attenuation than the attenuation that is actually allowed in the standard in order to accomplish the channel requirements. So before I move to the next slide, I want to also remind you that unless it happens, unless we have basically a whole fiber optic connection in optimal conditions to be connected with, let's say we have 8 fibers in a 12 fiber connector, 8 fibers working properly, right, with no attenuation, no issues, we are going to struggle actually to accomplish the 40 gig or 100 gig connection. In other words, we said at the beginning of the presentation that fiber connections, fiber links, don't support auto-negotiation. So what is going to happen is that if you don't have, in the case of 40 gig, the 8 fibers in your fiber link in good conditions, if only one of these fibers is dirty and is not, you know, in the conditions that are specified by the standard, the whole 40 gig link is not going to work. So we are not going to have 30 gig or 20 gig or 10 gig or wherever. We have either 40 gig or nothing, and this is where the MTP or MPO connections start to become critical. If only one of these connectors don't pass the specification, the criteria, you may really struggle to accomplish the connection and the connectivity between the two network points in the fiber link. So as the TIA is already recognized, let me advance a little bit the presentation. So we've been talking about the IC standard, right? We have a criteria that is defined for inspecting all the fiber optic end faces for single fiber connectors and multi-fiber connectors. And obviously, when it comes to test the installation, this is going to become now the first thing to do. Even before we get started with the Tier 1 certification tests or the Tier 2 certification tests, we are going to start always with fiber inspection. And this is what the TIA standard has recognized already. So in the new document of the TIA 568C, what you will see is that they are going to actually call the IC standard in order to inspect the test leads, the fiber optic end face of these test leads, in order to ensure a proper Tier 1 or Tier 2 testing. And this is kind of something new that we have, and it was recently approved, actually, a few months back, and that you are going to see in the next updates of this TIA document. So, if you are familiar with enterprise fiber testing and installation, you were typically forced in the past to do Tier 1 fiber certification or fiber testing. That is going to have an add-on now, which is going to be the fiber inspection part of the whole thing. So in this slide, we just want to show a little bit a test, right, of how an inspection of an NTP connector will look like. And as we said, we have defined a criteria, right? This criteria, acceptance criteria, is on the table. And in this specific connector, where we have detected a particle which is larger than 5 micrometers, obviously is not passing the specification because the standard specifies that in the cladding, we cannot have any particle larger than 5 micrometers. So this is the way that this standard is going to work in conjunction with a software, right, with an analysis software in order to analyze the fiber optic end face. Some more things to consider for this next generation networks. Obviously, I already mentioned that contamination is the first source of troubleshooting, but the worst thing is that this is going to have an exponential impact on the rest of the network. Let's say we have here a fiber optic connector, MTP connector, which is contaminated and is creating, let's say, 1-2 dB of loss, right? This 1-2 dB loss is going to be transmitted into the next part of the network, in this case, into this MTP cassette. So that means that all these fibers down here are going to be having 1 or 2 dB less, right? So that's why it's really, really critical to look at this aspect when it comes to install the fiber optic components. The impact can be exponential. So once we have cleared up the part of the fiber inspection, obviously you can start doing your testing, which you typically start with a Tier 1 fiber certification. The Tier 1 tests in the standards, in the TIA standards, are the only mandatory tests that you are required to do. And basically, you're probably aware of this, but basically this dictates to perform length and loss measurements. So in other words, we are going to check if the fiber that I have installed is accomplishing the requirements that I show you at the beginning of these presentations in the tables. So, as we said, we are going to set up a pass-fail criteria according to these tables for these couple of things, length and loss. So this is not going to change for future networks, for 40G and 100G networks. We are going to basically continue to do these Tier 1 certifications, but we'll have to look at some factors, some parameters that are going to really help us to accomplish successful testing when it comes to install this 40 gig or 100 gig. So referencing is one of these factors, right? So we are still aware that many people installing fiber are not referencing that this is really bad. Probably for the low speed networks, or for 1 gigabit Ethernet links, optical links that used to work if you have some kind of dirty connector, right? But as you have seen in the table, we don't have room for dirty connections anymore. So in 40 and 100 gig, we are talking about 1.9 dBs of budget, 1.5 dBs of budget. This is really very little. So referencing becomes more critical than ever. So we just put here some tips, some advices when it comes to testing. Like for example, what is the condition of the test jumpers? Some people, tend to inspect the fiber and the test, which is right, but they forget to inspect the test jumpers, which are also in the measurement, right, and can affect to the measurement. What is the right number of fibers to be used when referencing? This is up to the user and depending on, on the fiber type of your tester and the fiber type of or the connector type of your fiber under test. You are going to have to work with either one jumper referencing, or 2 jumper referencing, 3 jumper referencing. But the most important thing is to never disconnect the TX side after the reference, okay? So that's really matter, how many fibers you put in between in order to allow the whole connectivity in between your tester, your light source, and your fiber under test. But at the end of the day, things that the connectivity in the TX is critical. So if someone is not familiar with these measurements, basically this is typically performed with a light source and power meter. We are injecting light in one of the sides of the cable, and we are measuring this light injecting on the other side in order to check the total attenuation and then compare to the standards. So some more things that we have to take into consideration for performing Tier 1 certification tests is that the overall results can be even more accurate than testing with an OTDR if this test is done correctly. And what we mean by done correctly is the previous slide. If the test is done with the proper referencing and the clean leads and all this stuff around. So basically with an OTDR, we can get a very, very accurate measurements. But remember, with an OTDR, we are basically measuring the backscatter signal that is traveling back the fiber, and we are going to measure this, very small, level of power, let's say, from a fiber testing point of view. So when we are testing with a laser source and a power meter, we are actually reading an actual level that is being transmitted by laser source. That's why when we perform a Tier 1 fiber certification with a laser source and a power meter, we can even be more accurate than with testing with an OTDR, right? Only if we do it correctly. Some other considerations, like testing MPO and TP cables, may require a funnel cable in order to split this fiber into different fibers, and then the launch conditions into multi-mode fibers. So this is critically important. So in the past and even at present, we have been using these typical mandrels in order to kind of help to normalize the transmitter output level in the fiber, in order to not to overfill or underfill the fiber. And then we have a new technique, which is the encycler flux. There is a standard around this as well that is going to be very likely to be helpful in the future networks as well, in order to have a fully let's say an ideal fulfillment of the core of the fiber when it comes to inject light, in order to not to overfill or underfill the fiber, right, with more or less light. So the way that this is going to work is basically placing this encycler flux model controller right after the source, and this way, as I said, we are going to normalize this output level in order to have more consistent readings with our power meter. So we jump now into the tier 2 fiber certification, and basically what you see in here is kind of a representation of an OTDR trace, and from my testing point of view, nothing changes from testing a link for 1 gigabit or 10 gigabit or 40 gigabit Ethernet. What is going to change is basically the accuracy that you're going to have, or you're going to need to have in your OTDR in order to measure all these events. So what the OTDR is at the end of the day going to do is to measure the events like connectors and splices and fiber attenuation, and then the OTDR is going to compare these values obtained to the standards in order to give a pass or fail per event, right? So in this specific example, you have here a table, and you have here a green or red marks, depending on if the fiber that you are testing is within the standards or not. So things that you will need to consider for tier 2 testing is, for example, to have launch cables, to use launch cables if you want to characterize the first connector and the last connector. So typically for the first connector, you will use one of these launch cables, and as artifact that you will be using to characterize the last connector of the fiber, you will be using a non-reflective termination if you are working with single mode fibers, but this non-reflective termination don't exist for multimode, right? So for multimode, you will have to use things like this tail jumper using a PCI-PC connection in order to minimize the reflections, right? And obviously, it's really, really important to keep these tail jumpers and phase conditions in very good status. So some tips or advices that we want to give you from a tier 2 OTDR perspective. First of all, you will need to check the condition of the OTDR port. You will be surprised to see how many OTDRs we receive in our service centers that are having or are reporting issues in the connectivity of the OTDR port, and the only problem that they have is basically contamination. So it is highly critical in order to get an accurate measurement to keep the OTDR connector in good conditions. Also, two connectors too close may not be seen, and this is one of the things that we are going to have to consider for 40 gig and 100 gig networks. If you don't have, first of all, if you don't have a highly accurate OTDR, or you're not good enough interpreting the results, the OTDR traces, you may struggle to see and identify events that may be, for example, two connectors close from each other. This is the case of an NTP cassette. In the cassette, you may have in a even less than 1 meter two connectors, right? And these two connectors must be identified and measured if you want to fully characterize the whole fiber link. So in this sample, you can see one of these measurements, OTDR measurements that have been taken with one of our OTDRs, and yeah, basically we represent two very close connectors that are in a like 3-4 meters distance, and actually we are using a pulse of 2 nanoseconds in order to be more accurate in measuring these couple of events. And you can see very well represented these couple of connectors. You can even measure them, right? After each of the connectors, you have space enough in order to perform your measurements. So we wanted to share as well some real troubleshooting case using an OTDR. Why OTDR testing is important in enterprise networks, in fiber enterprise networks. Obviously, for the installation, Tier 1 testing, insertion loss, and length is kind of more than enough. But when it comes to troubleshoot, it's really complicated to identify the effective components, the effective connectors, if you are not using an OTDR. So here's where the OTDR becomes more important in the testing. That's actually a real case that we are representing here. That was a case where we have a couple of the data centers that were connected, and they were like a couple of kilometers distance from each other, and they were connected by a single mode fiber. Basically, these couple of switches, they were dropping the connection. This was basically a 10 gigabit Ethernet connection. And, the maintenance team responsible for this thing, they didn't actually know where the problem was coming from. After launching an OTDR trace, they discovered that this specific connector, as you see here, was having a huge attenuation. That was the connector number 5 that you see here represented. And actually, you see that huge drop that is represented here with over 8 dB of attenuation, something which is completely unacceptable. And obviously, that was making the whole system to fail, because the overall budget allowable was 9 dB. So that's just an example of how easy it is to identify defective components using an OTDR as a troubleshooting tool. So before jumping into some copper considerations, I'll go through this section very quickly. You have to know that we are going to have another webinar in a few weeks talking about this Tier 2 testing, OTDR testing. So I highly recommend you to register into that session and to join us in order to learn more about how to properly understand these Tier 2 certification tests and how to properly perform troubleshooting in enterprise networks. So we've been reviewing the fiber, which, as I said, is the biggest part of this presentation. And obviously, we cannot talk much about the copper for 40 and 100 gig, basically because we don't have a standard yet, right? So in this slide, we represent some of the, all the speeds and the cable categories that we have today in the market for supporting Ethernet over copper. And you can see basically that at the moment we are missing the 40G base T standard. As I'll explain a bit later, we have people working in the standard trying to define a proper solution, a proper standard to allow the 40 gigabit Ethernet signals over copper cables, twisted pair cable. And basically here we represent the different categories of cables together with the different applications that these cable categories work with, and also related to the frequency of testing and the tester accuracy, okay? So depending on what we talk about cable certifiers, there is a series of levels of accuracy defined in order to determine how far or how less you can reach in terms of frequency. And I'll speak a bit later about this. So basically, before moving to 40 gigabit over copper, we need to understand where we are today with 10 gigabit over copper, 10G base T. So now that we see the 40 gig Ethernet over copper in the horizon, it's when we are starting to see some explosion of 10G base T today, right? So some factors like those that you see here, the power budgets reduction, some things like the availability of network cards, energy efficient Ethernet stuff. I mean, there have been some milestones in the last couple of years that are driving this 10 gigabits Ethernet over copper, 10G base T technology to finally have a massive explosion deployment in enterprise networks and data centers. So there's just one small number here that we want to share with you. In the data center, 10G base T will grow from only 4% of media in 2010 to 44% in 2013. So as I said, looks like that now that we see the 40G base T standard in the horizon is when we see the final explosion of 10 gig base T. So where is the 40G base T now? Right. So there's been a lot of discussion and controversy about this topic in the last few months, a couple of years, I would say. And basically, a couple of things only that you have to know. It is demonstrated that we can transmit signals at the 40G, on a copper cable, twisted pair. That was demonstrated in the past with several studies performed by different universities and entities. And basically, there is some groups at the moment involved in the development of this 40G base T standard, right? So there are work groups defined at the TIA organization and also at the ISO in order to define things like, for example, what is going to be the bandwidth of these cables in order to support such a high-speed technology, or what is going to be the maximum distance allowed. So there is progress, and that's not going to happen overnight. Obviously, we are not going to have a 40G base T standard in 2012, but there are work groups defining the standards that are working in the definition of this 40G base T. So just to give you some information about the field testing and compare what we used to have in the past and what we are possibly going to have in the future is, as you see here, these bars represent the possible test frequency for 40G, right? And then the highest test frequency that we use today for the different cable categories. So we are talking about a maximum frequency of 1,000 megahertz today for a top category of cable like Class FA, right? The standards are talking now about extending this testing bandwidth up to, in the case of Cat 6, say 1,600 megahertz, and in the case of Class FA cabling up to 2,000 megahertz, which is obviously going to bring some complications when it comes to testing. So key technical issues that we are going to have for overcoming this or mitigate these problems that we are going to have. First technical issue is that obviously, the data rate is going to stretch the channel capacity of the available cable types. So the guys in the standards are actually discussing now the possible definition of a new category of cable, like it can be category 8 or stuff like this. But now the most immediate agreement is basically that they have to extend the bandwidth to either 1,600 or 2,000 megahertz in order to fully accomplish the definition of the capacity of that channel. Obviously, it's highly complicated to get better signal-to-noise ratio as we go up in frequency, but the easiest way is basically to increase the bandwidth available. So another technical issue that we are going to face for copper gig or 40 gig over copper, is that obviously the devices are going to become more and more hot, right? And the mitigation to this problem, we find it in the cable manufacturers. So there are multiple cable vendors around the world that are developing very good cabling solutions that may relieve some of these, PHY devices to get hotter and hotter and create complications to remove the informant. So finally, the insertion loss obviously is going to get worse as you increase the frequency, and obviously we can also have a mitigation to this problem, which is to specify standards that are shorter than 100 meters. So the current standard talks about 90 meters for the permanent link for copper, and these guys are defining now, are discussing, right, the possibility to reduce this distance to possibly 50 meters or 60 meters, which wouldn't be an issue for places like the data center, because most of the data center connections are shorter than this 50 or 60 meters in the copper side. And some of the tester challenges as well. Obviously, we have been talking about testing. There is no standard yet, but we need to get ready in order to, whenever this standard comes up, 40G over copper, to be able to test accordingly. So obviously, in the past, we used to see cable certifiers that had some limitations because of the internal hardware that were not able to support higher testing, higher frequencies testing, because of some internal limitations, hardware limitations. But the good thing is that at the moment and in the future, we'll have some new cable certifiers that are going to allow us to test up to such a high frequencies like 1600 or 2000 megahertz. And that's the end of the session today. So as a summary, it's clear that we have a need for speed in the enterprise networks and in data centers in general. And now more than ever, we'll need to have the physical media practically tested when it comes especially to fiber. And in the future, whenever the 40 gigabit over copper standard is defined, we'll have to keep up and define the same test procedures. So the fiber and phase condition is the leading cause of the loss in the fiber optic networks. You know that there is a standard to normalize this fiber inspection criteria, and this is going to become more and more critical in 40 and 100 gig Ethernet networks, and especially when using NTP and MPO connectors. As I said, copper cables will soon assist the gigabit Ethernet in testing, and the field testing will keep up, right? So I think this is the last slide where we kind of present the part of the JDSU portfolio for enterprise network testing, where we represent some of the copper and fiber cable certification tools for things like the certified 40G, for copper and fiber certification tier 1, and then OTDR platforms that are going to allow us to do the tier 2 certification testing. Sensing for connector and phase inspection, fully accomplishing the IC standards, and then active network testing in order to troubleshoot, all the active networks, and they help the IT managers and IT people to identify faults in the networks. And I think that's it. So I know, Carl, that I'm a bit over time, but I'm going to